Hello everyone, welcome back. Another data analysis video, and still looking at ANOVA, and I'm going to provide in this video just another example of how to conduct a one-way repeat measures ANOVA. This is going to include a little bit of tidying and cleaning data, a bit of data wrangling, some tests of assumptions. So I'll include it. I will show you how to conduct a Mortley's test of sphericity, and also to conduct post-hoc tests. Okay, so to get started, I'm going to import a number of software libraries that I'm probably going to use. I'm going to import pandas as PD, numpy as np, scipy.stats as stats, matplotlib.pyplot as plt, seaborn as sns, and pingouin as pg. So mostly I'm going to be using pandas, some numpy functionality, and pingouin. I'm not actually going to do any plotting. But to conduct these analyses, I'm mostly going to use the RM ANOVA method from Pingouin, and I'm going to import a data set to use for the analysis. So we're on a repeat measures design. So I'm going to create an object. I'm just going to say this RM_df, so repeat measures data frame. I'm going to import this data set using the pandas read_CSV method. The name of the dataset is hrpolygraph.csv, so it's saved on my computer as like a spreadsheet, comma separated value spreadsheet. And the data relates to a study looking at whether heart rate can be used as a representative measure of autonomic arousal in a lie detector test. So let me run that, and we'll look at what the data looks like. So there's 80 rows, so we've got 80 participants. And we've got three conditions: lie, truth, coloured squares. So participants lied, they told the truth, they took part in some control condition. I've used another data set for some of the previous analyses where the representative arousal measure was electrodermal activity. In this case, using a slightly different measure, we're looking to see if there's a difference if you use heart rate. When it comes to detection of lies. We've also got this framing variable. We're going to ignore that for now. But what we've got here is a short and wide data frame, essentially. So lie, truth, and coloured squares, these numbers, these floating point numbers here, all represent heart rate, like measures of arousal, using heart rate in some way. So as I've said in previous videos, I prefer to have the data in a long and thin format. So first of all, what I'm going to do is do a bit of data wrangling to tidy this up. So we have a column which represents the independent variable, the grouping variable, which is these questions, whether when asked a question did they lie, when asked a question did they tell the truth, and also this control task looking at coloured shapes, essentially some neutral task. So I'm going to change the data set so that we have one variable that has each lie, truth, and coloured squares as categorical variables with different levels, and then these arousal measures will all be under one variable with the name arousal or something like that. Mean arousal probably is the best name for it. So this data set contains a between subjects independent groups factor called framing. We're going to ignore that. It also contains a repeat measures factor that is currently split over those three columns: lie, truth, and coloured squares. At the moment, the column headers and the data underneath, the floating point numbers underneath, represent those measures of mean arousal taken from participants at three different time points: when they lied, told the truth, or complete the control task. Arousal was measured using the heartbeat, the participant's heart rate. And what I'm gonna do now in the next few cells is just kind of demonstrate. I've done it before in previous videos, but demonstrate how to transform that data set into a long and thin format. We use the pandas pd.melt method to do that. So first of all, I'm going to create a groups object with the three variables of interest, or the three groups of interest: lie, truth, and coloured squares. So I'm going to call that groups, so represent our grouping variable, and that is going to be our repeat measures data frame, and I'm going to pass it this list Note the double bracket notation, so I'm passing a list inside a list essentially, with the names of each of, they're currently shown as column headers, but there are different levels, different groups, different levels for the independent variable. So if we run that, what you can see here is if we call groups, we've just kind of extracted those 3 columns essentially. So now what I'm going to do is convert it to long and thin data using the pandas melt method. So I'm going to create a new object called cat underscore condition, so categorical conditions. And what I'm going to do is to create that, I'm basically just asking for a list. I'm going to use this groups object above and the column names. So groups.columns is the parameter I've put into there. So that's what that's going to, it's going to create a new object which has each of those represented against each participant, essentially each of the relevant column names or group labels essentially. And then to try to create a long and thin version of this data set, what we're going to do is I'm going to call it groups long, and we're going to use pd pandas.melt method, pd.melt, and the different things I'm passing are groups, which was the groups object we created above, the value underscore vars, so the value variable values that we're passing to it, and that's this cat condition object. The value name is going to be mean arousal, so that's our DV. So value vars is essentially our IV, our independent variable in this case. Value name is mean arousal, and I'm telling it to ignore the index in this case to start with. If I then call that new object, what you can see has happened is we've now got two variables. One, it's labeled variable because I didn't give it another name essentially, but this is our independent variable, and it's our categorical variable, our grouping variable. So lie, truth, and colored squares. It's compressed it down here, and then all those measures as they were before. These ones are now contained under the label mean arousal. So this is more informative really. When you have data in this format, the column name, the variable name, doesn't tell you anything about what it's recording essentially. When it's in long and thin format, you can see what these measurements relate to essentially. Okay, so one other thing I'm going to do is add an identity variable. So we've got these 2 columns. We told it to ignore the index. We told it to not ignore the index. And what we will do here is we're going to use the participant ID from the original data frame, this ID, and we'll just create a new participant number and append that to the end of our data frame. And that's all I'm doing here is I'm taking groups long, I'm appending a new variable called participant, and that's going to be the ID variable from our original data frame. So if we do that, if I call that variable again, the data set again, the new data frame, the long and thin version, you can see that's appended the participant identity number. So what we should see here is kind of 1 to 80 for the lie condition, 1 to 80 repeat again for the truth condition, 1 to 80 repeat again for the colored squares condition. So 240 times altogether. Okay, right. So I've got the data in this format now. Our groups long data frame here. This is how I want it to be able to manipulate it. So what I'm going to do first is run a test of assumption using Mauchly's test, and I'm going to use Mauchly's test of sphericity. I've demonstrated this in previous videos as well, and that tests the assumption that the variances of the differences of all possible pairs of within subject conditions are equal. So if we look at the differences between lie and truth for one participant, we're assuming they're similar to the differences between truth and colored squares, that type of thing. And if we violate this assumption of sphericity, then variance calculations may be distorted, resulting in an inflated F ratio. If the assumption of sphericity is not violated, we can assume the data is appropriate for use with a parametric or statistical test like ANOVA of the type we're going to conduct here. So I'm going to run this. I've done this separately. I've kind of run Mortley's test using the pingouin pg.sphericity method. And if you look here, we've got a number of arguments, parameters we have to pass in to that method. We've specified the data we want to use. We want to use this group's long data frame. Our DV is mean arousal. Our subject ID, so we have to count for the fact that participants contribute more than one data point, so it's a repeated measures design. So I've passed in participant, that participant ID number we created, and the within subjects variable, so the repeat measures variable is just it's currently labeled variable for want of a better name, and that's our kind of questions categorical variable. Okay, so if I run this, we get our results, sphericity results. We get an omega value, Mortley's omega of 0.88. We get a chi-square value of 9.82. Degrees of freedom are 2, and we get a p-value of 0.007. So using a kind of threshold for significance of 0.05, that convention that we usually have in psychology and many other kind of social science disciplines, you can see here we have a significant Mortley's test. So we've violated the assumption, or this data violates the assumption of sphericity. We've got a p-value much less than 0.05. So as a consequence, when we run the ANOVA, we would need to use some sort of robust p-value correction for the ANOVA test. And for this analysis, what we'll use is the greenhouse geyser corrected p-value. And we're doing that, it's convenient to do that because when you use the pingouin RM ANOVA method, it provides you that with that as part of the output. So let's do that. Let's conduct that now. Let's run the ANOVA, let's conduct the repeat measures as ANOVA, run the model, and then we'll look at what the output tells us. So here I'm creating a new object called results. It's going to be set equal to the pingouin repeat RM underscore ANOVA method. The data is our group's long data. The DV is mean arousal again. The within subjects factor is variable. Subject is part of the participant, so accounting for the fact that it's a repeated measures design. And I've specified detailed equals true. And if you remember from previous videos, what that does is returns this nice HTML pandas data frame or table, so to speak. Okay, so it's given us a number of different bits of output, of bits of information to allow us to interpret the model. Firstly, it's given us a sphericity. It's given us Mortley's test of sphericity and the p-value, and a boolean telling us it's false for us to assume sphericity. In this case, we knew that because we conducted it above. So I didn't need to conduct the test separately, but wanted to just demonstrate that you can do that. We could have just done the whole thing in one here, but wanted to just demonstrate how it's possible to do that separately. And in some cases, you might want to do that because you might be using a different sort of ANOVA method that doesn't give you this amount of output. It just gives you kind of some basic details, such as the f value and the p value. Looking at this, what you can see here is we have an f value of 3.14, and as I said before, we're going to use the greenhouse geyser corrected p-value. This is the p-gg-core, so p-value greenhouse geyser corrected, and we get a p-value of 0.051769. So if we could round that to 2, and it's slightly above 0.05. It's a very arbitrary cut-off point really for statistical significance. So it's slightly above, so technically it just falls outside that traditional alpha level for statistical significance that we use in classical statistics. But if we report it to 2 decimal places, we would claim this is significant, which is something that is frequently done. So as a consequence, if we were to say, okay, seems to be a significant F test, what we could do here is, what we would need to do is, if we're assuming this is a significant F statistic, we'd need to conduct post-hoc tests to follow up this ANOVA, because we have 3 levels essentially of the grouping variable. We need to know, what we want to know is which groups differ significantly from each other. So we've got three groups, so potentially 1, 2, 3 pairwise comparisons to make. And that, by doing that, we want to know, does lie and truth significantly differ? Does lie and the control conditions significantly differ? Does truth and the control conditions significantly differ? And because we're doing multiple comparisons when we're doing post-hoc tests, we need to use some sort of p-value adjustment. And I'm going to use the Bonferroni correction in this case to control for type 1 error when making these multiple comparisons. And the post-hoc method we're going to use, I've demonstrated in a previous video, the post-hoc method we're going to use is the pingouin pairwise underscore test method. So to conduct that, I'm going to create this new object called post underscore results. So post-hoc results essentially is what I'm abbreviating that to mean. And that's pg dot pairwise underscore tests is the method. So pingouin, there's a pingouin method that we're using called pairwise tests, and it conducts post-hoc pairwise tests. I'm passing in the data as an argument, and that's our group long data. Similar to above, we've got our DV's mean arousal still, our within subjects, our repeat measures factor is the variable, the grouping variable. Our subject factor is the participant ID number to account for the fact that they contribute more than one data point. We're saying we want parametric statistical tests, and the P adjustment here I'm using is short for Bonferroni. And the effect size that's also been specified is hedges, so that gives hedges G. So there are other effect size and P adjustments you can use. Look at the pingouin documentation in relation to these tests to see what they are. So if we run this and call the post-res object, it'll give us a nice table showing us the results. So what it's done is conducted 3 t-tests and adjusted the p-values to prevent us committing some type of type 1 error, or to reduce the possibility that we're thinking we've found a significant result when we actually haven't. Okay, so what you can see here is we've got coloured square, that's the control condition, compared to lie. We have a t-value of negative 1.63 if we round that, and a corrected p-value of 0.32, so that's not statistically significant. So it's got a negative sign in front of it, and this is just a function of which group was subtracted from which. So in this case, what we've seen here is that the higher mean was subtracted from the lower group mean, essentially. So we can largely, when you report t-tests, you can ignore kind of the negative sign and just report the kind of absolute value of the t statistic. Coloured squares compared to the truth condition, we've got a t-value of 0.80 and a p-value of 1. So that's obviously not going to be exactly 1, but we're definitely not statistically significantly different, almost identical essentially, these two in terms of the group means. And then lie compared to truth, we have a t-value of 2.25. P is corrected p-value is 0.08. So interesting thing to note here is if we'd have not used a robust ANOVA and used the uncorrected p-value, we would have considered this to be statistically significant. With the corrected p-value, I suggested this was kind of just falling above that, but let's pretend if we rounded it to 2, we could get away with claiming it's statistically significant. But what we're finding here is when we conduct these post-hoc tests and correct the p-values using the Bonferroni adjustment, that none of these groups are statistically significantly different from each other. Okay, so what this is telling us, it kind of fits with the actual findings that the p-value is just a good 0.05 is. The groups don't actually differ from each other, and if we'd not corrected and we'd have just used, so if we'd have used the uncorrected p-value for the F, for the ANOVA, and then used uncorrected p-values for these multiple comparisons, we would have been erroneously concluded here that lie and truth were significantly different because they have a p-value of 0.03. But that's not the case when we kind of make reasonable adjustments to try to ensure we're not committing some sort of type 1 error. Okay, so let me just read this last bit of text and we'll finish. So although we wouldn't normally conduct post-hoc tests when the ANOVA result wasn't significant, the fact the ANOVA model was close to that threshold alpha value meant it was probably reasonable in this case to conduct some post-hoc tests to try and identify if there were differences between those groups that may have been statistically significant. In this case, examination of the corrected p-values, though, so the p-core, the Bonferroni adjusted p-values, suggests there were no significant differences between the groups. And we'd report these comparisons like this. So color square versus lie, t bracket 79 is the degrees of freedom, equals 1.63, and p equals 0.32. Note I've missed the negative sign off that first one that appears there. Color squared versus truth, t brackets degrees of freedom 79 equals 0.80, p equals 1. Lie versus truth, t brackets 79 equals 2.25, p equals 0.08. So not statistically significant, any of those three comparisons. Fits with kind of the overall ANOVA result. So hopefully that was useful. What I've done there is demonstrate how to change the format of the data so it's long and thin, and then conduct Morchley's test of sphericity using the Penguin's sphericity method, run a repeat measures ANOVA, one-way ANOVA using the Penguin RM ANOVA method, and then because it was possible that we might have just been reaching this threshold of significance for this particular model, conducted pairwise t-tests with a Bonferroni correction, and that showed that there were no real significant differences between our groups. Okay, so that's another example of one-way repeat measures ANOVA. I'm going to do one more. I think I've got another example I will do, and then I think that's probably enough repeat measures ANOVA, and we'll do some kind of robust independent groups ANOVA, and then move on to factorial designs in the next few videos. Hope this was helpful. Thank you for listening.